Define the term unsaturated hydrocarbon. Right, so it is a hydrocarbon that contains a double or triple bond. Right, so that is 2.1. Let's look at 2.2.1. So let's write down the letter that represents an unsaturated hydrocarbon. So now we actually have to identify a unsaturated hydrocarbon from our list of chemical compounds. So let's look at compound A. We only have single bonds, right? So compound A is an alkane. It's an alkane. It's not a hydrocarbon. If it was a hydrocarbon, it would be an alkene or an alkyne, right? And then looking at compound B, we can see clearly here because of the OH that it is an alcohol, right? Alcohol. It is not a hydrocarbon. It also contains an oxygen. If you look at compound C, it also contains an oxygen, so it is not a hydrocarbon, right? Hydrocarbons only contain hydrogen and carbon, right? And then if you look at compound E, it says CXHYOZ. We have an oxygen, so it is not a hydrocarbon. So it's easy to see here using elimination that compound D is actually our hydrocarbon. Compound D is our hydrocarbon. You might be asking yourself, why can't I see the double bond or the triple bond? You're going to be able to see that when we do 2.2.4, we actually have to name that compound. But for the time being, just keep that thought to yourself. And then 2.2.2, let's write down the IUPAC name of compound A. Right, so let's pay all our attention to compound A and do some analysis. So it seems like this is not the longest chain, right? 1, 2, 3, 4, 5. That is not the longest chain, because when we name it, we have to look for the longest chain first. Let's try this chain right here. It looks really long. Let's try this chain and see what we have. There we go. So we're gonna have 1, 2, 3, 4, 5, 6. So we have 6 carbons if we follow that chain, right? And then it seems like it's our longest one. So if we have 6 carbons, we only have single bonds, and compound A is a hydrocarbon. Then we can say that the name is hexane. The name is hexane. And then after identifying that it is hexane, we can then, look at the branches and put them in our IUPAC name. So let's go ahead and look at our branches. If we start counting from this side, if we say that this is carbon 1, then we're going to have a branch on carbon 2. Right. Let's go to the other side and see what we have. If we say that this is carbon 1, on carbon 2, we don't have a branch. We only have a branch on carbon 3. Right. So it is wise for us to start counting from down here. This is carbon 1 and then this is carbon 2. So on carbon 2, we have a branch, right? 1 carbon. That is methyl. That is methyl. And then on carbon 3, 4, on the 4th carbon, we also have a methyl. We also have a methyl. So we can go ahead and say 2.4, right? Dash dimethyl hexane, right? And then just like that, we have the name of our compound A. Right, let's move to 2.2.3. So 2.2.3, it says that let's write down the IUPAC name of the positional isomer of compound B. So let's go ahead and look at compound B. We've already deduced that it is an alcohol, right? And then we need to find its positional isomer. So again, you need to know what a positional isomer is. So same molecular formula, but different position of the functional group. So all we have to do is take this OH and we put it somewhere else, right? If you put it on the first carbon, it's wrong because you have the same thing. You have to put it on the carbon in the middle, right? And then if we do that, we're gonna have those 3 carbons, and then our OH is now in the middle, right? And then we can fill out the hydrogens elsewhere. right? So this is the functional isomer of compound B, right? But then we're looking for the name and not the structure, right? But now that we have the structure, it will be easy for us to name. How are we going to name this? We're going to say propane tuol, right? Prop, from the fact that we have 3 carbons, and 2, the carbon where the functional group is situated, and all because it is an alcohol. 2.2.3 propane tuol, right? 2.2.4 IUPAC name of compound D, right? So that one you were asking me about earlier, compound D. So before we name this compound, let's write down the structural formula, right? Because it is a bit complicated naming if you don't have a structural formula, right? So the first carbon has 3 hydrogens, right? And then look at this, we have CH2, and then we have these 4 on the outside, right? So that simply means that we have 4 of CH2. So let's go ahead and put that in our equation, in our structural formula. So we have, there we have a carbon and then 2 hydrogens, right? That's the first one. A carbon, 2 hydrogens, a carbon, 2 hydrogens, and there goes the last one. And then now we can come to this CH right here. So let's have that CH. So C and then a hydrogen. And then we have this CH2 at the end. So we have C and we have 2 hydrogens. Right. You can see here that there's a bond missing. There's a bond missing. So what are we gonna do? We're gonna put a double bond here. We're gonna put a double bond. So that is the structure of that compound. But we're looking for the IUPAC name, right? So let's go ahead and calculate the number of carbons we have. So we have 1, 2, 3, 4, 5, 6, 7. So that is hept. So we're gonna have hept. The double bond is on the first carbon. The double bond is on the first carbon. So we're gonna have hept 1 in, because of the double bond, right? It is an alkene, right? Stories. Let's move forward and see what else we have. So 2.2.5, we're supposed to write a balance equation using molecular formula for the complete combustion of compound A. Right, so let's go ahead and do that. So compound A, we have 8 carbons, right? 6 carbons on the longest chain and 2 carbons as branches, right? So we can say that 2.2.5, we have C and then 8, right? Because those are 8 carbons. And then how many hydrogens are we gonna have if it is an alkane? We're gonna have 2n plus 2. Our n is equals to 8, right? So we're gonna have 18 hydrogens. We're gonna have 18 hydrogens. And then in combustion, it is plus O2 for us to get CO2 plus H2O. Right, so we're almost done. We just need to balance this equation. So here we have 8 carbons. Here we have 1. So we need to put a balancing coefficient of 8 there. So there we go, a balancing coefficient of 8. We have 18 hydrogens. We have 2 hydrogens. So if we put a balancing coefficient of 9, then we're going to have 18 on both sides. And let's go to oxygen. Here we have 8 multiplied by 2, that is 16. We have 16 oxygen, right? And then here we have 9. 16 plus 9 is 25. Yeah, so on the right hand side we have 25, on the left hand side we have 2, right? So it's easy to see that we need to put a balancing coefficient of 25 divided by 2. Let me show you. Let me just erase this so that it can be more clean. So we have plus 25 divided by 2, O2. Right, now the carbons, the hydrogens, and the oxygens are now all balanced. But then we cannot leave it like this. We cannot leave it with 25 divided by 2, right? We have to multiply out by 2. And if we do that, we're going to get 2 C8H18 plus 25 O2 to give us 16 CO2 plus 18H2O. Right, there we go. That is 2.2.5. Let's move to 2.3. So 2.3, the formula C4H8O represents two compounds that are functional isomers of each other. And then 2.3.1 is supposed to define the term functional isomer, right? So the same molecular formula but different functional group. And then in 2.3.2, let's write down the structural formula of each of these two functional isomers. So we have C4H8O, right? In general formula wise, it is CnH2nO. What is this general formula for? This general formula is for ketones and aldehydes because they are functional isomers, right? So if we go ahead and draw the structures, so we can start with the ketone. Let's start with the ketone. So we're going to have 1, 2, 3, 4, and then double bond oxygen, right? A hydrogen, and another hydrogen here. Right, and just like that, we are done with the ketone, right? Now we just need to draw the aldehyde. So for the aldehyde, so let's see aldehyde. We're gonna have 1, 2, 3, 4. And then the only difference now is that we have to put the double bond oxygen at the end, right? So if we put it at the end, it's no longer a ketone, but it is now an aldehyde, right? So there we go, hydrogen. Yeah, and just like that, we have answered 2.3.2, right? We have our ketone there and our aldehyde. The last question, 2.4. A 2-gram sample of compound E contains 1.09 grams of carbon and 0.18 grams of hydrogen. The molecular mass of compound E is 88 grams per mole. Determine the molecular formula of compound E by means of a calculation. Right, so let's go ahead and do that. So for compound E, we have, what do we have there? We have CXHYOZ, right? So we need to determine the molecular formula, right? So what are we gonna do? What is gonna be our first step? We have the masses, right? The first step is to calculate the number of moles, right? So let's just do that first, and then we're gonna carry on with that conversation. So the number of moles of carbon will be equals to the mass of carbon. It is given to us as 1.09, right? So we're gonna have 1.09 divided by the molar mass of carbon, which is 12. And then for the hydrogen, we have a mass of 0.18, the molar mass 1. And then for oxygen, we are not given the mass, but we are given the mass, right? We have three elements on our compound, right? We are given the mass of the 2 and the total mass. So it will be easy to find the mass of the third, right? We're going to say that the mass of oxygen is 2 minus 0.18 minus 1.09 divided by the molar mass of oxygen, which is 16. Right, so now we just need to go ahead and find this number of moles. So for carbon, I'm getting 0.09. So we have 0.09 for carbon. And then for hydrogen, it is going to be 0.18, right? That is easy to see. And then now we just need to compute the number of moles for oxygen, right? So let me just do that real quick. Why am I getting math error? Right, I forgot to divide by the molar mass. 0.0456, right? 0.0456. So the following step now is to divide this number of moles by the smallest of the three, right? So the smallest here is 0.0456. So carbon is to hydrogen is to oxygen is going to be in the following way. So let's go ahead and divide. So we divide in 0.09 by 0.0456, right? So if you say 0.09 divided by 0.0456, you're gonna get 1.97. So we can just take that as 2. And then for hydrogen, 0.18 divided by 0.0456, we're gonna get 3.94. We're gonna take that as 4, right? And then 0.0456 divided by 0.0456, that is just what? That is just 1, right? So we have oxygen, right? But then it doesn't end here. We're looking for the molecular formula. It doesn't end here, right? We have to take it a step further. We have to multiply out this ratio that we have by some number, right? But how do we get that number which is supposed to multiply this compound that we have right now with? We're supposed to divide the molecular mass of compound E that is given to us by the molecular mass that we have from this formula here, right? So we can say that X is equals to 88 divided by the molar mass of 2 hydrogens. How much is that? That is 12 multiplied by 2, which is 24. And then 4 hydrogens, 4, and then 1 oxygen, that is 16, right? So we have 88 divided by 24 plus 4 plus 16. That is equals to 2, right? So we know that we're supposed to multiply out by 2. If we do that, we're going to get C4H8O2, right? And now this is the molecular formula of compound E by means of a calculation. You might think that question 3 is easy. Well, it is in the sense that you can get a couple of marks, but then to get everything in this question is kind of difficult. Let's see what we have here. So let us investigate the boiling points of the 4 organic compounds given below. And then you can see the organic compounds there and their molecular mass. And then the first question, 3.1, let's define the term boiling point. It is the temperature. So it is the temperature at which Vp is equals to ATP. What am I saying? The temperature at which the vapor pressure is equals to the atmospheric pressure. That's what we refer to as the boiling point, right? It is not the temperature where liquid turns into gas. No. We don't say that anymore. And then 3.2, which compound, butane 1-ol or 2-methylpropane 1-ol, will have the higher boiling point? Fully explain your answer. So let's look at these 2 compounds and see how they differ. They're all alcohols, right? So they have the same kind of intermolecular forces, which is hydrogen bonding. But in butane 1-ol, you have 4 carbons in a straight chain. And then in 2-methylpropane 1-ol, you have 3 carbons in a straight chain and you have a branch, right? So that is how they differ. They differ in branching. So in order to answer this question, you have to know the relationship between branching, surface area, intermolecular forces, and consequently boiling point. So between these 2 compounds, butane 1-ol will have a higher boiling point. Why am I saying so? That is because an increase in branching, right? If the branching increases, then the surface area decreases, right? And then decrease in surface area decreases the intermolecular forces. And then if intermolecular forces decreases, less energy is going to be required to overcome the intermolecular forces, and consequently a lower boiling point. So the boiling point will also be lower. That is 3.2. Let's look at 3.3. So we are told that the curves P, Q, R, and S below were obtained from the result of the investigation. X represents a specific temperature, right? And then 3.3, the question is saying which physical property is represented by temperature X. So let's look at our equation one more time. What are we investigating? We're investigating the boiling points between these 4 organic compounds, right? And then you can see that X here on our graph, it corresponds with P, right? The graph for compound P. So what can you say the answer to 3.3 is? We're investigating the boiling point of these 4 compounds. That is the boiling point of P, right, from our investigation. And then 3.4, so we have 3.4 and 3.4.1, which curve P, Q, R, or S represents butanone. So let's take a different approach. So the first compound we have here is butanone, right? So let me just say, before we answer 3.4.1, let's do this first. So we have butanone, and we know that the intermolecular forces there is dipole, right? We have dipole. And then let's come to butane 1-ol. Yeah, the intermolecular force there is hydrogen bonding. So we have hydrogen bonding. And then propanoic acid. So we have propanoic acid. What is the intermolecular forces in propanoic acid? It is hydrogen bonding, but then it's 2 sides compared to butane 1-ol with only 1 side. So we also have hydrogen bonding here. But then the hydrogen bonding in propanoic acid will be way much stronger than the hydrogen bonding in butane 1-ol. Because in propanoic acid, we have 2 sides of hydrogen bonding. And then obviously, 2-methyl propane 1-ol, we know that that is hydrogen bonding, right? So the compound with the highest intermolecular forces of these 3 should be propanoic acid, right? So we have propanoic acid. And then what comes next? What comes next is butane 1-ol, right? So we have butane 1-ol. And then in third place, we have 2-methyl propane 1-ol, right? And lastly, we have butanone, right? So now we can actually attempt answering our questions, right? So which curve P, Q, or S represent butanone? So it will be the one with the lowest boiling point, and that is S, right? So we can say that 3.4.1, our answer is S. And then 3.4.2, propanoic acid, it should be the one with the highest boiling point. So that is P. And then 3.4.3, 2-methyl propane 1-ol. So it should be the one second from bottom, right? Should be the one second from bottom. So we say that S is butanone. So compound R should be 2-methyl propane 1-ol. So compound R is 2-methyl propane 1-ol. And then 3.5, let's give a reason for the answer in question 3.4.2. Why we say in P is propanoic acid, right? We know that hydrogen bonding is much stronger than dipole, right? But then the hydrogen bonding in propanoic acid is much stronger than the hydrogen bonding in the 2 alcohols. The compound here with the highest boiling point, with the strongest intermolecular forces, should be propanoic acid. And that is why we're saying it is compound P. What observable change occurs when you add bromine to an alkane? Does the container turn colorless or does it turn brown? That is 4.1.2. But let's just go ahead and do 4.1.1 first. The question is saying that which type of addition reaction is reaction 1? So let's go ahead and do some analysis. So we have reaction 1 here, and we are adding Br2, right? So we know that it is an addition reaction. But what is the name of that addition reaction? Because you are adding Br2, the name of that addition reaction will be bromination, right? So our answer for 4.1.1 should be bromination. bromination, right? If we were adding 2 hydrogens, then the answer would be hydrogenation. But then here we're adding bromine, so it is bromination, right? And then now for 4.1.2, one observable change that occurs in the container during the reaction. So when the reaction takes place, the color will go from brown to colorless. It will actually go from brown to colorless and not the other way around, right? So the answer to 4.1.2, the color of the container will go from brown to colorless, right? And then 4.1.3, the structural formula of compound Q. So we have compound Q right here, and then when we add Br2, one bromo is going to be on the first carbon, as we can see here from the name, and then another Br will be on the second carbon, right? So there was a double bond there. If we're adding them there and they go and stay in that location, it means that there was a double bond there, right? So we just draw in this the structural formula of this structure right here, but then instead of putting bromo on the first and second carbon, we're gonna put a double bond, right? Because that is compound Q before we add Br2. So what am I saying? I'm saying we have 1, 2, 3 carbons for propane, and then on the second carbon we have a branch which is methyl, right? So we need only 1 carbon here, and then now we say that when we add Br2, one Br will be on the first carbon and the other Br will be on the second carbon. So there used to exist a double bond there before we added Br2. So we're going to have a double bond here, right? And then everywhere else we can fill it out with hydrogens, right? So we need a hydrogens, it's saturated, and then 1, 2, 3, 4, that one is okay. And then the one in the middle, 1, 2, 3, 4, that one is also fine. So yes, this is the structural formula of compound Q, right? And now let's consider reaction 2, 4.1.4. Let's write down the IUPAC name of compound R. So let's go ahead and do some analysis again. So compound R is from compound Q, right? We add HCl in compound Q to get compound R. It is a bit confusing when you don't have a structure to actually come up with the name, right? So let me just go ahead and draw the structure, and then I can come up with the name. So let's copy this structure right here for the sake of time, and we're just gonna use that. So let's put it here. Yeah. So now that we add in HCl, this double bond, we're going to lose this double bond, and chloro is going to come here and hydrogen is going to come here. Hydrogen goes where there is the highest number of hydrogens, and then the halogen will come here in the middle because this carbon is bonded to the least number of carbons compared to this first one here. So this is the structure we're going to have at the end for compound R. So for this structure, we then need to give the name, right? So we know fully well that it is propane. We know fully well that it's going to be propane. And then on the second carbon, we have chloro, and then we also have methyl, right? So we're going to have 2-chloro-2-methyl. Yeah, it started to look messy there, but you can see what is going on. So we have 2-chloro-2-2-methyl propane. And that is the answer to 4.1.4. That is the IUPAC name of compound R, right? It's easy to make a mistake when you're naming. Let me just make sure that I'm not making any mistake. So on the second carbon, I have chloro, right? And then on the second carbon again, I have methyl, and then propane. We don't have to separate letters with a dash. So yeah, this looks fine because I cannot say 2.2 di something because I have a chloro and a methyl. If I had two methyls, I would say dimethyl. If I had chloros, I would say dichloro. But then I think this one is just gonna be like this, right? And then 4.1.5 for reaction 3 right down there. So let's go ahead and look at reaction 3. We have 2-chloro, 2-methyl propane turning into alcohol. So that is a saturated compound to a saturated compound. That is a substitution reaction, right? So let's go ahead and write a balance equation for that reaction that takes place. So 2-chloro, 2-methyl propane, we already have it here. So let's just go ahead and copy it again. Yeah, there we go. Let's see if we can pull it down. Yeah, we're good to go. We're good to go. So now I just need to remove these. Right, so there we go. We have the reactant in reaction 3, but we need to add something here that is going to remove this Cl, right? So what are we going to add? We're going to say, let me move it on the side just a bit. So we're going to say plus NaOH. We want to replace the Cl with an OH, but where will the Cl go? It will come here to the Na, right? So ultimately we're gonna have this will be our product. So this same structure again. So 1, 2, 3 carbons. We have a branch there, and then in place of Cl we now have OH, right? And then hydrogen, hydrogen, hydrogen. And then we need to fill out our hydrogens, and we're gonna have plus NaCl, right? And then we're good to go. You can use NaOH, you can use KOH. What else can you use? Yeah, you're not only restricted to NaOH, you can use other things too, right? And then 4.1.6, we need the IUPAC name of the alcohol. So the OH it's on the second carbon, right? So it's gonna be propane 2 all, and then now we just need to put the branch in our IUPAC name. So we're gonna have 2-methyl propane 2 all, and we are good to go, right? 4.1.7, we are looking for the type of elimination reaction in reaction 4. So we're starting with an alcohol and we're ending up with an alkene. That's dehydration. So we have dehydration. We're removing an OH and then H, right, to get that double bond, right? And 4.2, we have 4.2.1. So butane 1 all reacts with propanoic acid in the presence of a catalyst, rather than the type of reaction that takes place. So as soon as I see an alcohol and an acid, I'm thinking esterification. And then now we need the IUPAC name of the organic product formed. So the first part of the name will come from the alcohol, and the second part will come from the acid, right? So because you have butane 1 all, it will be butyl, and because you have propanoic acid, it will be propanoid. I only realized this not too long ago. So let's look at 5.2. So the question says that, let's consider the statement below. The rate of decomposition of N2O5 is half the rate of formation of NO2. Is this statement true or false? Give a reason for the answer. Do you know that you can actually use the balancing coefficient to find the rate of reaction of one compound if you have the rate of reaction of the other? I just only realized that not too long ago. It is exactly And it is exactly how we're supposed to answer 5.2 and 5.3.2. Right, so let's just do 5.1 first before we attempt those questions. So in the question statement, we are told that consider the following decomposition reaction that takes place in a sealed 2 decimeter cube container, and we are given an equation right here, right? And then it goes on to say that the graph below shows the concentration of N2O5 and NO2 change with time. Right, so if we look at our graph here, you can see that one graph starts at 200 and then it goes down to this point here, while the other one starts here and it is going up. And then the question, refer to the graph above and give a reason why curve A represents the change in concentration of NO2. So let's go to our equation and look at NO2. You can see that NO2 is one of our products, right? So our products, the concentration should be starting at 0, and this is exactly what we have here for this graph A. For this graph A, our concentration is starting at 0 and is going up. And then for the reactants, it is starting at 200 moles per decimeter cube and it is actually going down, right? So that is the reason why we're saying that curve A represents NO2. Right, and then moving to the second question. So we just did 5.1. Let's do 5.2. Consider the statement below. The rate of decomposition of N2O5 is half the rate of formation of NO2. Is this statement true or false? Give a reason for the answer. So let's go ahead and find out. What I was telling you earlier was that we can actually say that, let's look at our equation. We need to be basing everything on our equation, right? Let me just copy it down real quick. So we have 2N2O5 decomposing to give us 4NO2 plus O2. And then the question is saying the rate of decomposition of N2O5 is half the rate of formation of NO2. Right, so let's go ahead and figure out whether that is true or not, right? We can say that the rate of N2O5 divided by the rate of NO2 is equals to the ratio of their balancing coefficients, right? Here we have 2 for N2O5 and here we have 4 for NO2. So we're gonna have 2 divided by 4, and then the rate of N2O5 divided by the rate of NO2 will clearly be equals to 1 divided by 2, right? That is the same as 2 divided by 4. And if we cross multiply, you're going to get 2 multiplied by the rate of N2O5 being equals to the rate of NO2, right? And then if you make the rate of N2O5 the subject of the formula, you're going to get the rate of N2O5 being equals to half the rate of NO2, right? It is clearly half the rate of NO2. So our answer here is definitely true. The rate of decomposition of N2O5 is half the rate of formation of NO2. Right, you can see it from what I'm proposing here, that to find the rate of the other, while you have the rate of one, you can use the ratio of the balancing coefficient. Anyway, stories, let's do 5.3. We have another interesting one here. So 5.3.1, we're looking for the mass of NO2 present in the container at T is equals to 400 seconds. So let's go to our graph. Let's go to our graph. So we've already established that curve A is NO2, right? Is the concentration of NO2. And then in our equation, we're looking for the mass of NO2 present in the container. So I need to have a few steps that I know I'm going to take to find the mass of NO2. So from the graph, I can extract the concentration, right? And I'm given the volume in the equation. So with these two variables, I can find the number of moles, right? Concentration is equal to number of moles divided by volume. And then from the number of moles, I can ultimately calculate the mass. Only then, when I'm 100% sure of all the steps that I'm going to take, will I start solving the problem. So let's go ahead and do that. We're going to say that the number of moles is equal to the concentration multiplied by the volume. So let's go ahead and see how much concentration we have at T is equals to 400. So when T is equals to 400, you can see that our concentration is 200, right? We're looking for this curve A. Our concentration is 200. Well, not so quite. I want you to look at something. Look at our y-axis. We have the concentration, and the ISI unit is times 10 to the minus 4 moles per decimeter cube. So the concentration is actually not 200, but 200 times 10 to the minus 4, right? I hope you didn't make that mistake, because the first time when I tried solving this problem, I actually made that mistake and took the concentration as 200 instead of 200 multiplied by 10 to the minus 4. So if we use 200 multiplied by 10 to the minus 4, the volume is given to us as 2 decimeter cube, right? So we're gonna get 400 times 10 to the minus 4 being our number of moles. So now that we have the number of moles, we can go ahead and find the mass, right? We know that the number of moles is equal to the mass divided by the molar mass. So the mass will be the number of moles divided by multiplied by the molar mass I meant, and then this will be equals to, so what's our number of moles? Our number of moles is 400 times 10 to the minus 4, and then the molar mass of NO2. So the molar mass of N, nitrogen, that is 14, and the molar mass of O2 is 32. Right, now we are multiplying those two numbers we have right there. So let me just do that real quick and see what I get. So 14 plus 32 multiplied by 400 times 10 to the minus 4, I'm getting 1.84 grams. So right, that is the mass we have at equilibrium. It's actually supposed to be 1.84 grams. Right. Let's move to the following question. The average rate of production of O2 in moles per decimeter cube in 700 seconds. Right, so again, we're looking for the average rate of production of O2, right? But then we don't have a graph for O2 here. So to make our life easy, let's find the rate of production of NO2 and use the balancing coefficient to find the rate of production of O2. We can also use the rate of decomposition of N2O5, right? One between the two. So if we use the rate of production of NO2, we're going to find the change in the concentration divided by the change in time. So the concentration, it starts at 0, right? So this is our initial, and then our final at T is equal to 700. So 700 is somewhere here. So our final should be there. So let's go ahead and find that exact value. So from this point to this point is 50 units, right? 250 to 300, and we have 10 dots in between, so one dot is 5 units. So let's go ahead and find our concentration when T is equal to 700. So we have 250 here, 255, 260, 265, 270, 275, 280. So our final concentration is 280, and our initial concentration is 0, right? And then that divided by 700. Well, not 280, right? I'm making the mistake again. It's actually 280 multiplied by 10 to the minus 4, and then minus 0. right? Yeah, we should be aware of that. So 280 times 10 to the minus 4 divided by 700. And then let me just take this answer to scientific. If I do that, I'm getting 4 times 10 to the minus 5 moles per decimeter cube per second. So that is the rate of production of NO2. But what we're looking for is the average rate of production of O2. So we can say that the rate of NO2 divided by the rate of O2 is equals to the ratio of the balancing coefficient. So that will be 4 divided by 1. So the rate of O2 is equals to the rate of NO2 divided by 4. This will be equals to 4 times 10 to the minus 5 divided by 4. It should give us 1 times 10 to the minus 5 moles per decimeter cube per second. Right, so that is 5.3.2. And then 5.4. The Maxwell-Boltzmann distribution curve for the N2O5, so our reactant initially present in the container, is shown below. Redraw the curve on this. Redraw the curve above in your answer book and label this curve P. On the same set of axes, sketch the curve that will be obtained with higher concentration. So with higher concentration, the curve that should be obtained should look something like that. And now we just need to label it Q. Right. And then 5.4.2. Will the rate of decomposition of N2O5 at a higher concentration be higher than, lower than, or equal to the original rate of decomposition? Obviously, we know that it's going to be higher than, because if you increase the concentration, you're going to have more number of moles per unit volume, right? And then if that is the case, then more molecules will have a kinetic energy that is equal to or greater than the activation energy. More effective collisions per unit time. There's a lot of weird things in this question. For instance, 6.2.1, we have 1 mark being awarded, and 6.2.2, that is still the case. But 6.3.3 is out of 8 marks. It doesn't make any sense. Let me show you why I'm saying that. So 6.1, we are asked to state Le Chatelier's principles. So what it essentially says is that if an equilibrium is disturbed, then the system will favor the reaction that opposes that disturbance, right, in attempt to reinstate a new equilibrium, right? So that is 6.1. Let's go ahead and do 6.2 and 6.2.1 so that you can see exactly what I'm talking about. So if we go through our equation statement again here, you're gonna see that it says that 1 mole of pure hydrogen iodide gas is sold in a 1 decimeter cube container at 721 kelvins. Equilibrium is reached according to the following balance equation. So let's just copy down that balance equation real quick. So we have 2HI, and then we have H2 and I2. Right. So if we set up our table to calculate Kc, we're going to have something like the following. So let me just do that real quick. So here we're going to have the initial number of moles, right, on the first column, and then here we're going to have the change, and then here we're going to have the number of moles in equilibrium, and the last one we're going to have the concentration. So what we're given here is the initial number of moles of hydrogen iodide, right? It is said to be 1 mole, and then from there we're given the number of moles at equilibrium of I2. So the number of moles at equilibrium of I2, we have 0.11. Initially, we didn't have any H2 or I2, right? So we had 0 and 0 here. So it means that the change of I2 is plus 0.1, right? not 0.1 but 0.11. Yeah, so we have 0.11 here, and then that is the change in the number of moles of I2. But then the change in the number of moles of I2 is the same as the change in the number of moles of H2, right? So we can put 0.11 here. We're saying that they're the same because we have the same balancing coefficient. But then when we come here, because now we have 2, we're gonna have 2 multiplied by 0.11, right? Which is 0.22. So we have 0.22 right there. So with that 0.22, we can then find the number of moles of HI at equilibrium, right? So it's gonna be 1 minus 0.22. That's how you do it. And then in the product signs, you just add. So 1 minus 0.22, I'm getting 0.78. So we have 0.78. Here we have 0.11. So 6.2.1, we're looking for the number of moles of H2 at equilibrium. We're looking for the number of moles of H2 at equilibrium. So here they are 0.11. So we have 0.11 moles. And then the number of moles of HI at equilibrium, here they are. We have them now, right? We have 0.78 moles. Right. And all this work just for 1 mark. That's what I was talking about when I say, yeah, I don't really understand the mark allocation in this question. Maybe there's a quick way of finding those number of moles at equilibrium. You can say that for H2, right? But then for HI, you really need to, take it a step further to find those number of moles at equilibrium. But anyway, stories. Let's move to the second question, to the third question, by the way. 6.3.1. The equilibrium constant Kc at 721 kelvins is 0.02, and then the temperature of the container is now increased to 850 K. The equilibrium constant Kc is now 0.09. So it has increased with an increase in temperature. What does that mean? Let's go ahead. So the first question is the forward reaction exothermic or endothermic? It is endothermic. It is endothermic. And why am I saying that? 6.3.2. We need to fully explain that. So what we know, right, just from the basics, is that an increase in temperature, let's not forget, let me just write this first. Kc is equal to the concentration of the products divided by the concentration of the reactants, right? So if Kc increase, it means that now we have more products. Now we have more products. The forward reaction was favored. So the question is saying, is the forward reaction exothermic or is endothermic? The forward reaction is endothermic. That is because when the temperature was increased, we had more products, right? So it only makes sense that the forward reaction is endothermic. Because if you increase temperature, endothermic is favored. And as we can see that our Kc value has went up, we can clearly see that the forward reaction was indeed favored. Right. And then 6.3.38 marks. Right. Let's calculate the mass of HI present at the new equilibrium at 850 K. Right, so let's start with the initial number of moles. So the initial number of moles, we have 1, right, as we've already talked about. And then for H2 we have 0, for I2 we have 0, right? So we have that there. But then now we don't know the change anymore, because that change we had was for 721 kelvins. Now we're at 850. We don't know the change anymore, so we can put a variable in place of the change, right? We know that for the reactions you have to subtract. So let's say minus 2x, right? And then if this is minus 2x and we have a balancing coefficient of 2, then for H2 it should be plus x, because the balancing coefficient there is 1, and then plus x again, right? And then for hi at equilibrium, we're going to have 1 minus 2x. And then for h2, we're going to have 0 plus x, then 0 plus x. And now we move to the concentration. So the concentration, the volume is 1, right? And we know that concentration is equal to number of moles divided by volume. So the concentration will just be 1 minus 2x, x again. And now we have our concentration at equilibrium in terms of x. Yeah, we can go ahead and set up our equation, our expression for Kc. It will be the concentration of H2 multiplied by the concentration of I2 divided by the concentration of Hi squared. We're squaring that because our coefficient here is 2. Right, so let's go ahead and substitute. In place of Kc, we're gonna have 0.09 being equals to the concentration of H2, that is x, concentration of I2, that is x again, and then everything divided by 1 minus 2x to the power 2. Right, so we're gonna have 0.09 being equals to x squared divided by 1 minus 2x, 2x squared. So what you can do here, you can cross multiply and complicate your life, or you can take square root on both sides. Let's take square root on both sides so that I can show you what I'm talking about. So we can take the square root of 0.09, and then on the right hand side we can take the square root of this entire thing. So what is the square root of 0.09? That is 0.3. So we have 0.3 being equals to square root of x squared, that is x, and then in the denominator we're just gonna have 1 minus 2x. And just like that, we don't have a square anymore, because if we kept the square there, we would have to solve a quadratic equation, which is something I'm not really looking forward to. So if we cross multiply here, we're gonna get x being equals to 0.3, and then what is 0.3 multiplied by minus 2x? That is minus 0.6x. Right, so you can see that we can take this term to the left hand side. If we do that, we're gonna get 1.6x being equals to 0.3. So x is equals to 0.3 divided by 1.6. So what is 0.3 divided by 1.6? I'm getting 0.1875 moles. So the value of x is 0.1875 moles. But we're not looking for x, we're looking for the mass of Hi present at new equilibrium. The mass of Hi present at new equilibrium. So let's go ahead and find the number of moles of Hi at equilibrium. It's 1 minus 2x. So we can say that the number of moles will be equals to 1 minus 2x, but we now know what x is. It is 0.1875. So what is the number of moles? I'm getting 0.625, right? So we have 0.625. So we have the number of moles of Hi at equilibrium. Lastly, the mass will be equals to the number of moles multiplied by the molar mass. The number of moles is 0.625. I know that the molar mass of hydrogen is what? What's the molar mass of hydrogen again? I know that it is 1, right? How can we forget that? Now we just need the molar mass of I. That is 127, right? And then if I multiply those two, I'm getting 80 grams. Calculate the mass of ammonia in 1 decimeter cube of ChemClean. So the equation statement is saying that a concentrated household product, ChemClean, contains ammonia as the main cleaning agent. To determine the amount of ammonia present in 1 decimeter cube of ChemClean, the following procedure is followed. 20 centimeter cube of ChemClean is added to a 250 centimeter cube flask, then filled to the 250 centimeter cube mark with water, right, as we can see there demonstrated. And then the diluted solution is treated against the hydrochloric acid solution of the concentration as calculated in 7.2.1. So now we actually have to go to 7.2.1 and calculate that concentration. And then during the titration, 22 centimeter cube of the diluted ChemClean solution is neutralized by 18.7 centimeter cube of the HCl solution. So before we unpack this question, let's just go to 7.2.1 and calculate the concentration of the hydrochloric acid that was used. Right, so if we do that, you're going to find that in 7.2.1, we are told that a hydrochloric acid solution, HCl, is standardized by titrating it against 25 centimeter cube of a 0.04 moles per decimeter cube sodium carbonate solution. Right, so let's go ahead and jot that down, right? Because the formula that we're going to use should be guided by the variables we have. So our volume is 25 centimeter cube, and then our concentration is 0.04 moles per decimeter cube. Right. At the end point, it is found that 19.5 centimeter cube of HCl has reacted. So for the acid, we have a volume which is equals to 19.5 centimeter cube. And then 7.2.1, let's calculate the concentration of the HCl. So we're looking for the concentration. Right. And then if it is a standardization, then we can say that number of moles of acid divided by number of moles of base is equals to the concentration of the acid multiplied by the volume of the acid divided by the concentration of the base multiplied by the volume of the base. So what you put here in place of the number of moles is the balancing ratio, right? Because the actual values of the number of moles doesn't matter, because if you use the balancing ratio, even if you substitute the number of moles, you're still gonna get the balancing ratios, right? So what is the balancing ratio of the acid? We have 2. We can see it right here, and then that of the base we have 1. It's equals to concentration of acid, that's what we're interested in. The volume is 19.5, right, divided by concentration of the base 0.04 multiplied by the volume, which is 25. Right, now you might be asking yourself, why are we using centimeter cube and not decimeter cube? Because we are taking a ratio of the volumes, we can actually leave it like that. We don't have to convert it to decimeter cube, right? Only if we're using the ratio of the volumes, right? If we cross multiply, we're going to get 19.5 multiplied by concentration of the acid being equals to 2 multiplied by 0.04 multiplied by 25. And then if we divide both sides by 19.5, the concentration of our acid is going to be 0.1 moles per decimeter cube. That is 7.2.1. Now let's go back to 7.2.3. Right, so in 7.2.3, like we have deduced, we need to calculate the mass of ammonia in 1 decimeter cube of ChemClean. So let's go ahead and jot down the information we have so that we can use that information to see the formula we're supposed to use. So during the titration, 22 centimeter cube of the diluted ChemClean. So for the diluted base, now we are in 7.2.3. So for the diluted base, the base diluted, right? Which volume is used? A volume of 22 centimeter cube is used. And then what is it neutralized by? Now we come to our acid. It is neutralized by a volume of 18.7 centimeter cube of HCl, of which the concentration is the same as the one we calculated in 7.2.1, right? So that is 0.1 moles per decimeter cube, right? So we can start by finding the concentration of the diluted base. That's what we can start by doing, right? So if we go ahead and do that, we can say that the number of moles of acid divided by the number of moles of base is equals to concentration of acid, volume of acid divided by concentration of base multiplied by the volume of the base, right? So again, the balancing coefficients, here we have a 1:1, right? So if we substitute that, we're going to get 1 divided by 1 being equals to concentration of acid 0.1, volume of acid 18.7 divided by concentration of the base, concentration of the diluted base. That's what we want. Multiplied by the volume of the base, which is 22. So if we cross multiply here, we're going to get 22. Concentration of the base being equals to 0.1 multiplied by 18.7, right? So now, as you can clearly see there, it is just a matter of dividing both sides by the coefficient of our base, right? So the concentration of the base will be equals to 0.085 moles per decimeter cube, right? There we have it. We have the concentration of our diluted base, right? But then we want the mass of ammonia in 1 decimeter cube of the concentrated chem clean, right? This is where this formula comes in. Concentration of the concentrated solution multiplied by the volume of the concentrated solution should be equal to the concentration of the dilute solution multiplied by the volume of the dilute solution. So we're saying that the number of moles in our concentrated solution is the same as the number of moles in our dilute solution, right? So let's go ahead and find the concentration in our concentrated solution so that we can ultimately find the number of moles and end up calculating the mass of ammonia in 1 decimeter cube of chem clean. So the concentration of the concentrated is what we're interested in, and then the volume of the concentrated is 20 centimeter cube, right? So we're gonna have 20 right there, being equals to the concentration of the dilute, which is 0.085 multiplied by the volume of the dilute, which is 250. So it should be quite obvious what we're supposed to do now. We're going to divide both sides by 20. And if we do that, the concentration of the concentrated will be equal to 1.0625 moles per decimeter cube, right? So this is the concentration of the 20 centimeter cube, but it's the concentration of the 1 decimeter cube also, because we're just using 20 centimeter cube of the 1 decimeter cube, right? We're not changing anything with respect to how concentrated or diluted it is, right? So now we can go ahead and say that the number of moles in 1 decimeter cube will be equal to concentration multiplied by volume. The concentration is 1.0625 and the volume is 1 decimeter cube. So the number of moles will be equal to 1.0625 moles, right? But then we're looking for the mass, and we know that the number of moles is equal to the mass divided by the molar mass. So the mass will be equal to the number of moles divided by the molar mass. The number of moles, that is 1.0625, and then the molar mass, so is the molar mass of what? NH3, that is 17, and if you multiply that, you're gonna get 18.06 grams of ammonia in 1 decimeter cube of chem clean.